When you first look at advanced physics, there is this expectation of terrifying calculus.
Oh, absolutely.
Like you look at a whiteboard covered in integral symbols, Greek letters, and vector notations, and your first instinct is just to run the other way.
Yeah, the math panic is real.
Right. But then you stumble across something like Gauss's law, and suddenly all that terrifying calculus kind of melts away into simple geometry. So today's mission is all about decoding exactly why this foundational physics principle actually works.
It's a really beautiful transition, honestly.
It really is. And we have a 13-slide presentation on electric flux and Gauss's law right in front of us. We're going to walk through it slide by slide so you can follow right along with us mentally on this deep dive.
And, as we go through this, think of Gauss's law as the universe's ultimate accounting system.
Okay, I like that.
Yeah, it isn't just some equation to memorize for a final exam. It is a fundamental ledger. It's
Yeah.
a set of rules showing exactly how the physical world balances its invisible forces. Once you understand the underlying mechanism of that accounting, the math stops being abstract. It becomes incredibly intuitive.
Okay, let's unpack this. Opening up the presentation, we start with slide 1, which is titled Mapping the Invisible. And it sets our visual language for the rest of the deep dive.
Mm-hmm.
Right in the center is this transparent sphere, and it's being completely pierced through by a series of parallel blue arrows.
Right, so those arrows represent electric field lines.
Okay.
Physicists use these lines to basically visualize the direction and the strength of an electric force. And the critical thing to remember throughout this entire discussion, the absolute rule, is that the denser the grouping of arrows, the stronger the electric field.
Got it.
It just gives us a way to conceptually grab onto a force that we otherwise, can't physically see.
Which makes sense, because we need to figure out how to measure that invisible force as it moves through space. And that brings us to slide 2, the flux catcher.
Ah, yeah.
This slide introduces our core concept, which is electric flux, represented by the Greek letter phi sub e.
Yeah, so electric flux is fundamentally a measure of flow. Specifically, it's the flow of a uniform electric field passing perpendicularly across an imaginary surface area.
Okay.
So the underlying formula on the slide is phi sub E equals E times A. You are simply taking the strength of the electric field, your E, and multiplying it by the area it passes through, your A.
To ground this for everyone listening, think of holding a square net in a flowing river to catch water. Or, and maybe even better, imagine raising a square sail to catch the wind.
That's a great way to picture it.
Right. If the wind is blowing at a constant, steady speed, which represents your uniform electric field, and you have a sail of a very specific size, multiplying them tells you exactly how much wind you are catching.
Exactly.
That captured wind is your flux.
The sail analogy works beautifully because it highlights the transfer of energy across a boundary. Like the wind has kinetic energy, and your sail intercepts a specific cross-section of it.
Right.
In physics, we are measuring the electric field lines penetrating a defined boundary. But that straightforward E times off formula relies on a highly idealized assumption.
Because it assumes your sail is facing perfectly square to the wind.
Exactly. And the real world isn't like that.
No, the physical world is rarely that accommodating.
Yeah.
The wind changes direction, or, you might not hold your net perfectly perpendicular to the river's current.
Right, you get tilted.
Yeah, so we have to account for that geometry. Let's shift to slide 3, the geometry of interception.
Here is where we introduce the angle of interception into the math. It's represented by the Greek letter phi.
Okay.
So the equation updates to phi sub E equals E times A times the cosine of phi. And the slide visualizes 3 distinct states for our imaginary net.
I see them.
First, there's maximum flux, where the angle is 0 degrees. The net is perfectly square to the flow, intercepting the maximum possible number of field lines.
Then you have a state of reduced flux, where the net is tilted relative to the flow.
Exactly. And finally, zero flux. This happens when the net is tilted a full 90 degrees, rendering it perfectly parallel to the flow of the field. The wind just blows right past the edges of the sail without catching any fabric at all.
The field lines never pierce the boundary.
Right, not a single one.
Let's look at how this behaves with real numbers by moving to slide 4, application. The tilted disk.
This is a good practical example.
The setup here is a disk with a radius of 0.1 meters, and it's sitting in an electric field that has a strength of 2 times 10 to the third newtons per coulomb. When the disk is perfectly perpendicular, our maximum flux is roughly 62.8 newton meters squared per coulomb.
Right, so that establishes the baseline. The geometry is fully engaged with the field.
But then we see the tilted scenarios.
Mm-hmm.
Tilting that disk by 30 degrees drops the flux down to 54.4,
Mm-hmm.
and at 90 degrees, it drops to 0.
So I had a question about this.
Go for it.
From the perspective of the electric field lines, does a tilted disk literally just look like a smaller target?
Mathematically, yes, absolutely.
The cosine function in the equation is literally just calculating your effective cross-section. When you tilt the disk, its physical dimensions obviously stay the same, but its footprint from the perspective of the oncoming field shrinks.
It's like looking at a coin edge on.
Exactly. The math is just adjusting for the fact that fewer field lines can physically intersect that boundary.
So catching flux with a single flat net makes total sense.
Mm-hmm.
But, the universe operates in 3 dimensions.
Right.
What happens if we drop a fully closed 3D box into that same electric field? To explore that, let's advance to slide 5, the closed system paradox.
This is where the mechanics of vector fields really start to challenge our basic intuition.
Yeah, because the slide features this imaginary cubical surface, just resting inside a uniform horizontal electric field.
And look at the calculations mapped out on the faces of this cube.
Right, the flux entering the back where the surface normal vector opposes the field at an angle of 180 degrees is negative E times A. But the flux exiting the front face, where the normal vector aligns perfectly at 0 degrees, is positive E times A.
Mm-hmm.
Meanwhile, the top, bottom, left, and right sides are all parallel to the field lines. They sit at 90 degrees, which means they catch 0 flux.
So when you tally the ledger for that entire 3D shape, you add negative EA and positive EA plus a bunch of zeros.
And the total net flux is exactly 0.
Exactly 0. The net flow into any closed space in a uniform field strictly equals the flow out.
I can accept that for a box perfectly aligned with the field. But let's flip to slide 6, the rotated cube integration.
This one looks a little scarier.
It displays the exact same cube, but now it's been tilted by a random angle, beta. Now every single face is catching a fraction of the field. The math on this slide is just a dense thicket of sine and cosine components.
What's fascinating here is that it looks completely chaotic, right?
Very.
But the underlying geometry forces order on that chaos. Even when you tilt the cube and you are forced to calculate complex trigonometric components for every individual face, they perfectly cancel out. Wait, really?
Every single time. The angle is totally irrelevant. The net flux of that closed system remains absolute 0.
Okay, I have to push back on this though. If the net flux is always 0, no matter how we spin the box, isn't this entire concept completely useless for actually measuring anything? Like, we just spent 6 slides proving that the final answer is always nothing.
It feels like a trick, right? But that 0 result is actually the secret to everything that follows.
How so?
Because it proves a profound rule about conservative vector fields. An electric field merely passing through a space does not alter the ledger. What enters the boundary must exit the boundary. The only scenario where the net flux will be anything other than 0 is if the actual source of the electric charge itself is physically trapped inside your imaginary box.
Okay, that flips the script entirely. The box only cares about what it contains, not what passes through it.
Precisely.
That brings us to slide 7, which introduces the core thesis of this whole presentation. Gauss's law, the ultimate cheat code. And the visual here is super striking. Instead of a neat cube or a perfect sphere, the slide displays a messy, amorphous, potato-shaped blob.
Yeah, it's pretty ugly.
Very. And inside this highly irregular boundary is a chaotic mix of positive and negative charges, marked as plus Q and minus Q.
And right below that blob is the master equation. Phi sub E equals Q enclosed divided by epsilon naught.
Going back to our concept of the universe as an accountant, this equation represents the ultimate ledger.
Good.
It essentially dictates that the complexity of your boundary does not matter at all. The shape can be infinitely irregular. If you tally the net electric charge trapped inside that specific volume, you know the exact total outward flow of flux.
Here's where it gets really interesting. It reminds me of a highly secure bank vault.
Oh, I like this.
You don't need to stand outside the bank trying to calculate every single dollar bill passing through the hands of the tellers or, being withdrawn from the ATMs outside.
Right.
If you possess the master ledger of exactly what was deposited inside the vault, you know exactly what the vault is worth. The chaotic activity at the boundary doesn't change the net reality of what is enclosed.
That is a perfect analogy. The boundary dictates how the flux is distributed locally, sure, but it cannot alter the total sum.
Right.
But to truly test that logic, we need to push the physics to an extreme.
And we do exactly that by moving to slide 8, the expanding sphere paradox.
This is a fun one.
This slide sets up a thought experiment that directly challenges my intuition, frankly. We start with a small positive charge of +3 microcoulombs, enclosed in a sphere with a radius of 0.2 meters.
Okay.
Then the sphere expands, the radius doubles to 2r.
And the math dictates that the total flux remains completely unchanged, which I admit often feels wrong at first glance.
Yeah, my intuition is screaming that if the sphere gets twice as big, the surface area gets vastly larger. And we established earlier that flux is field strength multiplied by area.
We did.
So if the net gets exponentially huge, shouldn't it catch more total flux? How does the ledger stay balanced?
To understand the physics here, we have to look at what physicists call the cancellation rule.
Okay.
It's deeply tied to the geometry of three-dimensional space. When you double the radius of a sphere, its surface area doesn't just double.
Right.
It increases by a factor of 4 because surface area scales with the square of the radius. So your net is indeed 4 times larger.
Which seems like it should just break the equation.
It would if the electric field remained uniform. But electric fields, much like gravity, radiate outward in 3 dimensions.
Oh, right.
Because they're spreading their influence over the 2D surface of a 3D sphere, they obey the inverse square law. As you move away from the source charge, the field strength dissipates rapidly, proportional to the inverse square of the distance.
So the expansion of the boundary is simultaneously weakening the field it's trying to measure.
Precisely. If we connect this to the bigger picture, at double the distance, the electric field strength drops by exactly 1/4.
Oh, wow.
Yeah. So when you calculate the final flux, you are multiplying an area that is 4 times larger by a field that is 1/4 as strong. The geometry of the expansion perfectly cancels the dissipation of the field.
Because 4 times 1/4 equals 1.
Exactly. The total Gaussian flux remains strictly tied only to the enclosed charge, regardless of whether your imaginary sphere is the size of a marble or the size of the solar system.
And the math just autocorrects based on the physics of 3D space.
The universe balances its ledger using the geometry of space itself.
That is genuinely fascinating.
Yeah.
So how do physicists apply this autocorrecting math to physical materials? Let's turn to slide 9, symmetrical application 1, solid spheres.
So here we are looking at 2 different types of real-world materials, a solid conducting sphere, like a block of copper, and a solid insulating sphere, like a ball of solid rubber.
Okay.
The physics of how charges behave inside these specific materials completely changes how we apply Gauss's law.
Looking at the slide, for the conducting sphere, the electrons are free to move. Because like charges repel, they push against each other until they are distributed along the absolute outer edge of the ball.
Right.
Consequently, if you draw an imaginary Gaussian sphere anywhere inside that copper ball, your enclosed charge is 0. The internal electric field is just 0.
But in an insulating sphere, however, the charges are locked in place.
They can't migrate to the surface.
Exactly. They remain uniformly distributed throughout the material's volume. So if you draw an imaginary Gaussian surface inside the rubber ball, you are trapping a fraction of those charges.
You have to use a volume ratio to figure out exactly what percentage of the total charge you've enclosed.
Which means the internal field grows steadily as you move from the center outward.
Got it. Okay, let's complicate the geometry even further and jump to slide 10, mapping the hollow conductor.
This is a classic textbook problem.
The visual here is pretty complex. It basically looks like a cross-section of a jawbreaker. In the dead center, we have a solid core carrying a +2q charge. Surrounding that core is an empty vacuum gap. And enclosing that gap is a thick, hollow shell made of conducting material that carries a -q charge.
Now, calculating the electric fields for a nested structure like this using traditional calculus would be incredibly tedious.
I can imagine.
But Gauss's law simplifies it if you analyze the system region by region.
It's essentially like peeling an onion. If we look at the empty gap between the core and the shell, an imaginary Gaussian sphere drawn in that region only swallows the core.
Right.
It is entirely blind to the outer shell. Therefore, the enclosed charge is just +2q, and the field behaves as if only that central core exists in the universe.
The physical boundary of your Gaussian surface isolates the variables, but the real power becomes apparent when you evaluate the system from the outside.
Let's see. If we draw our imaginary sphere large enough to swallow the entire jawbreaker, we enclose both the plus 2q core and the minus q shell. Yep,
And the ledger simply adds them together. Plus, 2q minus q leaves us with a net enclosed charge of just q.
exactly. By zooming out and encompassing the entire system, you can treat this intricate, multi-layered hollow object as if it were just a single, simple point charge of Q suspended in empty space.
That's incredibly elegant.
It is. The internal complexity is completely abstracted away by the boundary, and real-world engineering relies on this exact principle. It is the fundamental physics behind Faraday cages, where external fields are canceled out by the surface charges of a hollow conductor, protecting whatever is enclosed inside.
Which brings us to the ultimate utility of this principle, avoiding complex math altogether.
My favorite part.
Let's flip to slide 11, symmetrical application 2, the infinite wire. The problem presented here is a wire that extends infinitely in both directions, possessing a linear charge density denoted by lambda.
Now, trying to calculate the electric field of an infinite wire by integrating the contributions of every microscopic charge along its infinite length is a grueling exercise in advanced calculus.
Yeah, most do. But Gauss's law offers a bypass, provided you can construct the right imaginary boundary. The slide demonstrates trapping a segment of the wire inside a Gaussian cylinder.
The text here highlights a technique called exploding the integral, because the electric field radiates straight outward from the wire in all directions perpendicularly to the wire's length. The flat circular end caps on the top and bottom of our imaginary cylinder catch zero flux.
Right. The angle is 90 degrees, so the cosine is 0.
So the only portion of the cylinder that physically intercepts the field lines is the curved outer surface.
Exactly. Instead of doing calculus, you simply calculate the area of that curved surface, which is the circumference 2 pi r multiplied by the length, and you just drop it into the algebraic formula.
That's almost too easy. And we see this identical strategy applied on slide 12, symmetrical application 3, the infinite sheet.
Yes, another classic.
Now the problem is a giant, endless flat plane of charge with a surface charge density of sigma.
Right. And for an infinite plane, a cylinder won't work the exact same way. The trap requires a different geometry, a piercing pillbox.
A pillbox.
Yeah, imagine a small cylindrical box pushed halfway through the infinite sheet, protruding equally on both sides.
Because the electric field from a flat sheet pushes straight away from the surface, the curved sides of the pillbox run parallel to the field lines,
Exactly.
so they catch zero flux. The only surfaces intercepting the field are the two flat end caps pushing out on either side. So the relevant area is just 2e times a.
You've got it.
So to make sure I understand the broader implication here, we aren't actually doing calculus in these scenarios, are we? We are intentionally inventing imaginary geometric shapes specifically designed to ensure that 90% of the surface area yields a mathematical zero, just so we can bypass the physics and solve the problem with basic algebra.
That is a highly accurate assessment. It is a mathematically sanctioned cheat code.
That's wild.
You are leveraging the innate symmetry of the physical universe against itself. By matching the geometry of your imaginary boundary to the symmetry of the source charge, you isolate the active variables and literally erase the rest.
Well, let's bring all of these tools together by turning to our final slide, slide 13, the Universal Symmetry Toolkit. This basically summarizes our entire deep dive into a reference table.
It acts as a final index for the logic we've discussed. For a point charge or a uniform sphere where the field radiates outward in all directions, your tool of choice is the concentric sphere.
Right.
For an infinitely long wire where the field radiates cylindrically, you deploy the coaxial cylinder. And for an infinite flat sheet, you utilize the piercing pillbox.
You simply select the shape that aligns with the symmetry, you cancel out the faces that parallel the field, and you solve the remaining algebra.
It's beautiful. I want to read the final quote at the bottom of this slide, as it encapsulates the profound shift in perspective Gauss's law offers.
These do.
It says, symmetry transforms calculus into geometry. By choosing the right lens, the invisible becomes perfectly measurable.
So what does this all mean for you? When you step back from the formulas and the Greek letters, the core mechanism of Gauss's law reveals a deep physical truth.
It really does.
It demonstrates that the universe's ledgers are always perfectly balanced. The apparent chaos of complex charge distributions on the surface is just an illusion. You just have to know how to draw the right imaginary box to perceive the underlying order.
And I want to leave you with a final thought to mull over, returning to that concept of the ledger. We just spent this entire analysis examining how Gauss's law makes the math beautiful and easy by using perfect cylinders, perfect spheres, and perfect pillboxes to cancel things out.
Yeah, we exploited symmetry.
Exactly. But recall slide 7, the slide featuring the chaotic, ugly, amorphous blob,
The potato.
the potato. That slide proved that the total flux is still absolutely tied to the enclosed charge, even when the shape possesses zero symmetry and the math is way too complex to easily calculate.
The ledger remains balanced, regardless of whether we have the symmetrical tools to easily read it.
So here is the provocative question to ponder. Is Gauss's law merely a clever mathematical trick humans invented to solve symmetrical problems? Or does it hint at a deeper, unshakable law of conservation woven into the architecture of spacetime? A law that holds absolute truth even when the physical world is too messy and we are physically incapable of doing the math to prove it.
The X-ray machine of physics might expose a complex, highly irregular world, but the underlying geometry governing it is flawless. Thank you for joining us on this deep dive into the mechanisms that shape our reality. Keep questioning the things you can't see, and keep exploring the invisible forces around you. We'll catch you next time.